All right. Hey, everyone. Welcome back. It's Mr. D here today. Today we're going to be doing lessons 5.10 and 5.11. They are the last two lessons in Unit 5. So far we've talked a lot about transformations in this unit. Today we're going to be putting all of that together and seeing if we can apply it to real-world type scenarios. So in this first task, they give us a graph. It is the temperature of a bottle of water as it's removed from the fridge and time goes on. So it started off really cold and increases in temperature. They also give us this table of values on the right-hand side here. The first thing it wants us to do is go ahead and enter the table of values into a graph in Desmos. So I already have my Desmos open in another tab here. I'm going to go ahead and tab over into Desmos and start entering values. So in case you don't know how to get to the table entry part in Desmos, I just clicked plus here and then went down to table. Once you do that, it'll open up a table for you to start typing your values into. So our first x value is 0, our y value is 35, so I'm just going to go ahead and type that in. Our next x value is 0.4, and the y value is 42. I'm just going to continue typing in these values until I get this entire table entered in here. Okay, so at this point I have the rest of my table typed in. You can see on the right-hand side that the table shows up in Desmos, but you'll have to rescale your axes so that you're able to see it. When you first open Desmos, you're going to be too zoomed in, so just make sure that you zoom out so that you can see your entire table here. Now that we have our table entered, let's go back to the lesson document and see what exactly we have to do with this. So it tells us for each of the following function types, and it tells us those are quadratic, exponential, radical, and rational function. It wants us to use Desmos to apply a sequence of transformations to our function so that it matches the data as well as possible. So what that means is we're going to be taking one of these parent graphs here, typing in just the parent graph into Desmos, and then applying a sequence of transformations to that graph to try and make it go through these points as much as possible. So let's see if we can do that. Our first graph was a quadratic. So I'm going to go into Desmos and just type my equation, y equals x squared. We can see right now it definitely looks like nothing like this set of data points over here. Before we can make it look like these data points, we're going to have to apply a sequence of transformations. So what transformations do I want to apply? Well, if we think about what this set of points kind of looks like, to me it kind of looks like half of a parabola, just upside down. So I'm thinking the first thing I'm going to want to do is flip this entire parabola upside down so that the top part of it right here, or I guess right now it's the bottom vertex, when it flips up, will kind of go through these points. So I know that putting a negative in front of my x squared here will reflect this over the x-axis. In other words, just flip it upside down. So I'm going to start by typing that negative there. But now we're still too low. We can see that right here, my highest point on my inverted parabola is 0. And the highest point on this series of dots that we're trying to match the table to is 70.5. So the next step is going to be to transform, or translate, I should say, translate this entire parabola up 70.5 units so that the highest point matches over here. I know that just adding a number to my equation here will shift everything upwards. So I'm going to do plus 70.5, see what that looks like. Okay, so that looks decent. We're getting closer. We're matching the highest points together now, but my parabola is still too far to the left. I'm going to want to slide this entire parabola over to the right next so that the vertexes here fall on top of each other. So if I look at how far my rightmost point is, I can see that it's at the x value of 5. I also know that adding or subtracting numbers inside of the, I guess we didn't see them before, the invisible set of parentheses here will move my graph to the left or right. I want to move to the right, and as we know at this point, subtracting numbers moves my graph to the right. So since I want to go 5 spaces, I'm going to subtract 5 from my x inside of the parentheses. Okay, so as we can see now, my graph is almost there. The only difference is it is too wide. As we can see, these points curve down a little bit more. So I'm going to go ahead and multiply something to the outside of this set of parentheses here to try and shrink up or narrow up the outer edges of that parabola. I don't know what exactly the number I want to try first is, so I guess I'll just do 2 to begin with, and we'll see where that puts us. Okay, so it looks like multiplying by 2 shrinks it a little bit too much. So instead of 2, I'll try 1.5. That looks pretty good. Let me try maybe one other number, 1.4. I like that one the best so far. I think that this equation matches the set of data the best out of all of them. So now that we know what our transformed equation is, I'm going to go ahead and copy this and then write the transformed equation over here where it's asking for us. Oh, that doesn't look very clean at all. Okay, I guess I'm just going to have to type it out again, which is no big deal. I'll be right back as soon as I have that typed out. And there it is written out. The equation that we found matches this data best by transforming our quadratic graph. So I'm going to do the same thing for each of these other parent functions now. We just found what we would have to transform a parabola by in order to make it match our set of data. Next, we're going to try an exponential equation. So we've got our parent graph is e to the x equals 2 to the x power. I'm going to go back to Desmos and type that in over here, and then we're going to mess with it and see if we can make it fit our data set. Okay, so just looking at our starting graph here, I noticed that we have the same issue that we were running into when we first typed in our quadratic function, and that's that it's facing the wrong way. We can see that this one starts off very close to 0 and then starts increasing. We're going to want something that increases and then kind of tops out around where our top point is. So the first step in getting our graph to look a little bit closer to that, I think, is going to be to put a negative in front of it, to flip it upside down. We know that we want it to curve around in this direction anyways, so I'm hoping that by putting a negative, we'll get something that looks a little bit closer to that. So now our function's been reflected over the x-axis, but I noticed that the curve is still moving the wrong direction. We want it to come up on the left and then kind of flatten out as it moves to the right. Currently, it is already flat on the left and then starts curving as it goes further to the right. So in order to change that, we're going to have to reflect across the y-axis as well. In order to do that, we know that we can replace all of our x's or whatever variable we're dealing with the negative version of itself. Here, since our variable is x, I'm just going to replace that x with a negative x. So now we have negative 2 to the negative x as our function. It's now been reflected over both the x and the y-axes. So the next thing I'm noticing about this graph is that it's too low. Again, here our maximum value is slightly below 0. And on our table here, we know that our maximum y value is 70.5. So we're going to have to shift up a little bit to get there. I know that the graph here stops increasing much after we hit x equals 5. So adding a number close to 70.5 should get us close enough to top out at about where we want to. So I'm just going to add 70 to mine, and we'll see how that looks. Okay, there we go. That looks like about the right maximum value. The next thing that I want to adjust on here is we're starting too far to the left. We're going to have to shift a certain number of spaces to the right here. So in order to shift to the right, I know that I want to, on an exponential equation, add or subtract something from the x in the exponent up here. So let me go ahead and start by trying 6. Oops, that is not right. If it'll let me type in here, that is. Okay, so that looks like maybe I went a little bit too far here. I'm going to try again with a slightly smaller number. Let's try 5 and see what happens. Okay, we're getting closer. If there's anything else at all that I want to change about this graph, it's that it might be a little bit too stretched out. I want to compress it just a tiny bit. And the way that we do that is by changing the number that's being raised to a power of x, so the base number here. In this case, it's a -2. I'm going to increase it a little bit, see if we can compress enough. Let's go, instead of -2, I'll try -3. Okay, so that, as you can see, moved us far too far over. I'm going to try it again with a number that's closer to -2. Let's try -2.1. Okay, that looks about right. Maybe we're a little bit too low here, so I'll bring it just a tiny bit closer to -2. We'll try -2.05. And now I think that looks just about perfect. So this is the equation that I'm going to copy down and write back on my lesson sheet over here. I'll be back with you guys once I have that written down. So I've got my equation written down here now. Y equals -2.05 raised to the negative x minus 5 power plus 70. So our next type of function is a radical. The base form example that they gave us is x to the 3/5. Really, it could be x to any kind of fractional power here. So let's go ahead and type in our parent function that they gave us into Desmos, and we'll see if we can make it match our data. All right, so I've got my equation typed in over here, but as you guys can see, it is much too squished down here. The y-axis is being compressed way too much. So the way that we can stretch our graph vertically is by multiplying a coefficient in here in front of the x. So I'm just going to start picking numbers and multiplying them in and seeing if we can get them to some place that looks close to where our data is here. Let's try 5 first. Gets us a little bit closer, but not enough. Let's try a bigger number, maybe 10. Still not there. 20. 50 looks like it went too far. I'll try 30 instead. Okay, so we're at an interesting situation here where the graph is passing through one of the points, but as we can see, it's sliding down too quickly. Our points have more of a gradual descent as we approach the y-axis, whereas our graph here just kind of shoots down towards the origin. So I think that 30 is going to be too large of a number as far as a vertical stretch goes. Instead of trying to just stretch it vertically to reach this, I'm instead going to add something to the end of it that will translate us up in the positive y direction, and hopefully we'll be able to get there closer to that. So I'm going to go back to a smaller number over here first. 20 looks like the shape of the curve is about right. It's just too low. So now I'm going to start adding numbers over on the right-hand side of my equation and seeing if we can translate this graph up enough to where it looks like it's in about the right spot. So let's just start by adding 10. Looks like it's still too low, so I'll add 20 this time. Still too low. 30. Still too low. Okay, so if I were to get tired of guessing and checking different numbers here, I'll go back to our original graph. What I could do is look over on my table here and see that my first point on the table is 0, 35. So that's going to be this point right here in Desmos. So I know that this graph already passes through 0, 0. If I want to make it pass through 0, 35 instead, I can just add 35. That'll shift everything on my graph up 35 units, and we'll be passing through that point perfectly. Okay, so now we're going through the first point just right. The only issue is it looks like my 20 value that I picked for the vertical stretch is still a little bit too drastic. So I'm going to bring that down a little bit to see if I can stretch it out less so that it'll hopefully line up on top of these values over here. Let's try 15 and see what that does. Okay, so we're getting closer. There's not a lot else that I think I would want to do to this graph, We could try maybe playing with the exponent up here and seeing if we can change the exponent to make it line up a little bit closer. Let's try, just as an example, 4 over 5 instead of 3 over 5. So that won't work very well because having an even number up there, as you guys saw, makes it, instead of continuing downwards, it bounces up. So we'll try a different odd number. 1 out of 5 flattens it up too much. 7 out of 5 makes it stretch a little bit too much. So for this one, I'm happy with keeping just the 3 out of 5. I feel like it matches the data well enough that we're able to use this equation. Although I still think that our exponential equation and our quadratic that we did earlier fit the data better. So if you were actually being paid by someone to try and model this data set, you would probably try all these different types of equations and then decide on one that's not exponential because it might not fit as well as the other data sets that we used did. Okay, but with that aside out of the way, I'm going to go back to my lesson sheet and copy down my new equation that I know works for a radical function, or a rational function, I should say. And there we have our equation, y equals 15x to the 3/5 power plus 35. Okay, so our very next equation is going to be rational. Our parent function that they give us to work with is f of x equals 1 over x. So I'm going to go back to Desmos and type in our parent function. Okay, so as we can see here, this type of graph has an asymptote at y equals 0. What that means is that the graph is going to approach 0 the further and further away it gets from the origin. As we home in on an x value of 0, the graph shoots downwards on the left-hand side and upwards on the right-hand side, moving towards negative and positive infinity. So I'm going to start by noticing that I want my graph to be increasing as it moves to the right. So the first thing I might want to do is reflect this over one of the axes. Interestingly, in the case of a rational function like this, it doesn't matter which axis we reflect over because they're already, as you can see, if we were to reflect over the x or the y-axis, we would end up at the same point. So to keep it simple, I'm just going to do a reflection over the x-axis, that is a vertical reflection, and I'll do that by just sticking a negative in front of my graph here, or in front of my equation, I should say. Okay, but even after we've done the reflection, you can see that the graph is still much too sharp. I'm going to try and adjust that by multiplying a number inside of the parentheses here. So we don't really see the parentheses, but I'll put them in here just so that it makes a little more sense. We could either multiply the number over here where my cursor is in front of the entire graph, or we could multiply it by the numerator. It doesn't really matter which. I'll show you. If I were to type 2 right here, or let's use a bigger number so the difference is a little clearer. If I were to type 20 on the outside, or if I were to replace my numerator with 20, we end up with the same graph. I'm going to go ahead and write it in the numerator up here. If you guys would rather write it over in this space to the left of your fraction bar, that's also fine. So what I'm trying to do now is make this section of the graph on the second quadrant, that's the bottom right, line up with this curve over here. It looks like 20 maybe isn't quite enough, but to make it easier to see if it's matching, I know that this is going to be translated up in the end anyways. So I'll go ahead and do my vertical translation right away. Let's think about what number we might want to add here. I'll start by just picking one and seeing how much we move. So 10 looks like it was not nearly enough. Let's try adding a larger number. We'll try 30 next. Still not enough. 50 maybe. We're getting there, but I think we could go a little bit further. Let's try 60. Okay, that looks close. Maybe still not quite there. 65? All right, I like that for now. We might not keep that 65 number. Doesn't look like it's quite there yet, but now I'm going to go back and start tinkering with this 20 again to see if I can stretch it out a little bit more. As you can see, a lot of what I'm doing here is just, I don't know exactly what number is going to work. I know where I can put different numbers to affect the graph a certain way, but I don't know what the right number I want there is. So I'm doing a lot of trial and error. we'll go try 30 here. That stretched it out. Oh, that's 300. 30, yeah, that's a little more reasonable. It still looks like it might be a little bit too sharp of a turn here, so I'm going to go a little bit bigger. Let's try 60. There we go, doubling it. Looks like it about did it there. Now, as we can see, about the same angle that these points are curving down at, our graph itself over here is curving at. So I notice that we're a little bit far to the right here. If I want to shift to the left, I know that I'm going to have to add or subtract something to x inside the parentheses. Remember, adding numbers moves us to the left and subtracting moves to the right. Since I want to go left here, I'm going to be adding. So let's try +1 and see where that puts us. That's a little bit closer, but I think we're still maybe not quite far enough. We'll do 1.5, see where that puts us. Okay, now we look like we're about right as far as our x values go. Our y values are also a little bit too small. So instead of 65, I'm going to add a larger number to shift us up a little bit more. 70 is close. 75 looks about right. So by applying all of these transformations, shifting up and down, left and right, stretching the graph out by multiplying by a number in its numerator, and so on, we were able to adjust the original parent graph to look about like what our data looks like. So again, I'm just going to copy this equation down on our lesson, and I will be back with you as soon as I have it written down. And there we have it, y equals -60 over x plus 1.5 plus 75. So again, all we were doing for this section was taking this set of data that they presumably gathered from the real world. They tell us it's from measuring the temperature of water after it's been removed from a fridge, and took several kinds of parent functions, applied a bunch of transformations to those parent functions, and made the graph look like this. So if you're wondering why we would ever do this, say there was some kind of chemical that you have to keep cold or else it becomes unstable. Well, what we did when we have an approximation, I'll go back to Desmos so we can see what this looks like, of what the graph might look like if we were to fit something to this data. That lets us see what the temperature would be at any point. So if I zoom out here, I can see that, say, 20 minutes after the water has been removed from the fridge, it's going to be about 72 degrees. So just a reason for why we learned that. Okay, so the next part of our lesson wants us to describe how well the model fits our data. So originally, none of the models fit at all. Afterwards, we had models that more or less fit the data, but some might have fit better than others. So what you can do there is talk about how well each individual model ended up fitting the set of points that we were given, and tell us which one you think works the best. So even if you had slightly different equations than I did here, just go ahead and base your answer off of your own. Tell us which type of parent function you were able to transform to fit the data the best. Was it the quadratic, exponential, radical, or rational? So pause the video, do that, and then we'll move on. Okay, so next we'll take a look at task 2. This one is titled, How many books can one person have? So they give us this table, and it tells us that it shows us the values of two functions, p and b, where p of t is the population in the US T years after 2010, and b is the number of books sold T years after 2010. So the first thing it wants us to do is use the table that they've given us to plot the values of b as a function of t. All that means is use t as the point on our t-axis, use b as the point on our vertical axis here, and we're going to go ahead and plot all of these points out. So our first point is 0 and 2530. I'll go ahead and put a point right here because our t value there is 0 and our y value is 2530. Our next point is 1 in 2400. So that'll be right about here. And I'm just going to continue this process until I have all of these points plotted out on my graph. I'll be right back with that. All right, so I've got all my points plotted out on the graph here, and it wants to know, what does this tell us about book sales? So remember, in the prompt here, it tells us that B is the number of books sold in millions since the year 2010, T years after 2010, I should say. So if we look at our graph here, 0 years after 2010 and 1 year after 2010, there were 2,530 and 2,400 books sold respectively. So we saw a bit of an increase there. Then 2 years after 2010, so this would be in 2012, our book sales increased quite a bit, all the way up to 2,720. And then after 2012, we remained more or less constant. We didn't go up or down a whole lot on any of these. It's more or less a flat line. So if I want to interpret that, I could say something along the lines of book sales increased from 2010 to 2012, but then remained mostly constant from 2012 to, and our ending value here is at 6. That means 6 years after 2010. So 6 years after 2010 is 2016. Okay, so looking at number 2, it says how many books were sold per person in 2010 and 2016? What do these values tell us about book sales? So in order to know how many were sold per person, we're going to also need to know what the population is. In our prompt up here, it tells us that P is the population. So in the year 2010, we sold in millions 2,530 millions books when there were 309.35 million people in the United States. So that means to find my books per person in 2010, what I'm going to do is divide the number of books by the number of people. So 2,530 divided by 309.35. And that comes out to, according to my calculator, that comes out to 8.17. So what that tells us is per person, there were 8.17 books sold in the year 2010. We'll do the same thing to find the books per person in 2016. This is the one it was asking us about, right? Yeah, 2016. So there were 2,700 books sold. Really, that's 2.7 or 2,700,000. But since our data is given to us in millions, I'm just going to keep it in that form. And we're going to divide that by the population, which was 323.41 million. So according to my calculator, 2,700 divided by 323.41 is 8.34. So for each person, there were 8.34 books sold in the year 2010. So the next question is, feel free to copy this work down in this section as well if you want to show how you got your values there. So what does this tell us about book sales? Well, it tells us that more books were sold per person in the year 2016 than in 2010. Okay, so we found that by looking at these two separate functions, and we were able to get values for what the books sold per person were by dividing the number of books sold by the number of people. For number 3, it wants us to complete this process for all of our values and use that to define a new function. So it says define a new function R, I'm guessing R for rate of books sold, by R of t equals B of t divided by P of t. So that's exactly what we were doing up here. Then it says complete the table and then graph the values of R of t. Make sure to label and title the vertical axis. What do the values of R tell us? Okay, well, we already found two values of R. In 2010, R, when we did that division, gave us 8.17. And in 2016, it gave us 8.34. So I'm just going to go ahead and continue doing this division on each of these other cells. So just take B divided by P for each of these and fill out all of my R columns. I'll be back with you guys as soon as I have that done. All right, so I'm back now with my table filled out. Let's go ahead and see what it wants us to do with the values of that table. It says graph the values of R of t, making sure to label and title the vertical axis. So as far as what I'm going to title the vertical axis, that's up to us really, but we know what it's telling us, right? R, we divided the number of books by the number of people. So I'm going to label this axis as books sold per person. And our horizontal axis, the t-axis, is already labeled for us as the time in years since 2010. Okay, so we know that all of our values here are between, our lowest value is 7.7 and our highest value is 8.7 about. So how many cells do we have here? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to start with my lowest value being 7.7. And then I'm going to try and increase slowly but surely to get to my highest value, which is about 8.7 here. So we'll do 7.9 for the next one. 8.1, and so on until I've fully labeled this axis. So I'll be back once that's all the way labeled. All right, so I've got my vertical axis fully labeled here. The next step is going to be to plot these points on the graph. So my first point, t is 0, r is 8.17. So I'm just going to go ahead and plot that on my graph here. When t is 0, r was 8.17. So that's going to be a little bit under halfway between 8.1 and 8.3. When t is 1, r is 7.7, so that's going to be all the way down here at the bottom. When t is 2, r is 8.69, so I'll plot that one next, and then I'll just continue with that process until I have each of these points plotted on the graph. All right, I'm back with all of my points plotted. So it doesn't ask us to draw a line of what r could look like, but let's just say it did. If we wanted to draw a line through this graph, it would look something like that. Okay, so what did the values of r tell us? Well, we know that this graph is telling us the number of books that were sold for every person in the US. So let's see if we can interpret this data. So it looks like in the years 2010, or over the course of the year 2010, I guess I should say, before the start of 2011, our books sold per person decreased. Then there was a brief increase from 2011 to 2012. And then ever since 2012, the number of book sales has gone down. If we take a look at the number of books sold, we know that that remained about constant, but we can see that the population went up every year. So even though the number of books sold stayed about the same, because the population was increasing, the number of books sold per person decreased. So I'll go ahead and write something like that in this box. But your explanation doesn't have to be exactly the same as mine. The one I came up with was the number of books sold per person decreased from 2010 to 2011, but increased from 2011 to 2012. Then they started decreasing steadily from 2012 onward as book sales remained constant, but the population increased. So with that out of the way, we'll look at our final task for today. Task 3, adding functions. So in this task, they give us several graphs, and each graph has this same graph E on it, and then a different graph. In the first one, it's L, and the next one, it's M, and then N, and so on. What they want us to do is define a new function S, where S is equal to the sum of E and whatever other function is being added. In this case, it is L. It wants us to, on the same set of axes, sketch what we think the graph of S looks like. So when we're adding two different functions together here, really what that means is check what the output is for each function at any given input value and just add the outputs together. We can see that we only know what E is defined as for values greater than -2. As soon as we get to values smaller than -2, the value of E is too high to see on the graph anymore. So when I'm sketching my sum, I don't know what the value of E is for anything less than -2, so I can't add E to something else. So really all I'm going to be doing is looking at values that are greater than or equal to -2 when I'm doing this problem. We can see at the value -2, E is up here at 7, whereas L is at -1. If we were to add 7, sorry, I misspoke, at -2. If we were to add 7 and -2 together, we would get +5. So that means the value of S, which we get by adding the two of them together at -2, is going to be -5. So I'll put a point on my graph right there. I'm going to do the same thing for several other values of X. Sorry, forgot what variable we were talking about there for a second. For several other values of X. And I'm going to see if I can get an idea for what that sum graph might look like. So let's just try 0 for one of our other values. I can see that L is at 0, E is at +1. 0 plus +1 is still just +1. So my output will be right there at 1. We'll try 2. I can see that E is just ever so slightly above 1 when X is 2, and L is at 2. So we're adding 2 to a number that is just a little bit bigger than 1. So that's just going to be a little bit bigger than 2. Sorry, did I say 1? I meant 0. It's not bigger than 1. It's just a little bit bigger than 0 is what I meant to say. I'm going to keep doing this process for several other values of X until I think I know what the graph might look like. So I'll be back once I've tried this for several other values. All right, so I went ahead and repeated that process for 4 and 6, and then I wanted to know a little bit more about what would happen at -1. So I just added the outputs of both E and L when X is -1, and I got a number that is in between 1 and 2. So now I have an idea for what this graph would look like. It wants us to sketch it, so in order to do that, all I'm going to do is complete the dots on this graph here. So it'll probably look something, oops, let me redo that a little bit. Something like this. So we were able to make a new function S by adding the outputs of E and L together. We're going to be doing the exact same thing on each of these other graphs. So for our first one here, E and M, I can see that M is equal to -1, or outputs -1, no matter what value of X we're inputting. What that means is each of these values of E, when we add -1 to them, is just going to be one smaller, right? So I'm going to go ahead and plot 1 less than whatever the current output value is of E is for each value of X. Oops, that's a bad one. And you can see that just like E is starting to approach 0, our new graph S is starting to approach -1 as we move to the right. So my new graph then will look just like the graph of E, except everything is shifted down 1 unit. Like so. If you guys prefer having less messy graphs and drawing them over on this graph to the right, by the way, you are more than welcome to do that. We gave you a clean set of axes that you can use if you want, but if it's easier for you to just draw it on top of the same graph, that's also fine. These notes are for you, so whatever you think works better. Looking at E and N, I'm going to do the exact same thing. N is just a line with slope -1 that goes through the origin. So all I'm going to be doing is finding what the value of N is for each input and adding or subtracting that number from E. So if we look at the input of -2, E is at 7, N is at, what is that, +2. So when we add those together, we'd be at 9. It's going to be a little bit off the axes, but that's okay. I still want to put where the point about would be. When X is 0, N is 0, and E is +1, 0 plus 1 is still just 1. When X is 2, E is a number slightly larger than 0, N is at -2, so -2 plus some small decimal number is just going to be a number slightly larger than -2. And I will continue this process for a few other X values until I think I know what the graph is going to look like. Okay, so I went ahead and plotted out 2 additional values of X. I think I have enough information now to go ahead and try drawing my graph. So my graph will look something like that. All right, so at risk of this video ending up too long, I'm going to leave these ones for you guys to try on your own if you'd like. We do them exactly the same as we did the first 2 parts of number 2. Just check what the output is and add the 2 outputs together to get your new function. Thanks for taking the time out of your day to watch this lesson, guys. Again, if you have any questions, feel free to email me. My email is at the top of the page here, tylerdewhurst@gmail.com, or Mr. Cardenas. He also does office hours and tutoring, so if you would like to attend one of his scheduled tutoring sessions, feel free to do that. If you need to make an office hours appointment with him, feel free to do that. I'm sure that between the 2 of us, we'll be able to answer whatever questions you guys have. Hope you're all staying safe out there, and have a good rest of your day.